Tiago Silva is next up on for the last talk in this session. So Tiago, it's over to you from the University of Brazil.
Hi, can you hear me?
You hang on just a second. I need to. That's good.
Hi, can you hear me?
Yeah, we can hear you. Okay, good. So this is,
hi everyone.
I guess, a talk now into normal intelligence rather than artificial intelligence, I guess.
Yeah, that's
classification. Okay, over to you.
Hi everyone, my name is Tiago Silva. I am glad to be in this session. I am a supporter for the use of artificial intelligence and the processing of IBA spectra, but today I'm going to talk about different things. Today, I prefer to talk about PIXESim. This is a feature requested by many users of MultiSIMNRA. And so far, I had no date of release of this software, and this presentation will not give you an answer for that yet, but at least it will give you a glance of the future. So basically, my presentation is divided into three topics: why we need another PIXE software. Then I'm going to talk a little bit about the PIXESim philosophy, what we decided to implement, and then we're going to show some validation. So basically, why we need a PIXE software? Well, you may have been informed about MultiSIMNRA. It is a computer program that enables self-consistent analysis based on SIMNRA calculation. Because of that, we can only implement self-consistently scattering techniques like RBS, ABS, ERD, and NRA. It has a robust and free of bias objective function and a statistically sound evaluation of uncertainties. Even if you use SIMNRA for a unique measurement, it's interesting to learn how to use MultiSIMNRA to take advantage of the advanced optimization methods and the evaluation of uncertainties. But basically, MultiSIMNRA does not include PIXE. To talk a little bit about the software we need, we have to check out what's the normal procedure to analyze a scattering technique. That defines how MultiSIMNRA works. Basically, we have to rely on a forward model because in general, RBS doesn't allow you to do the inverse calculation. It means that having the spectra, you cannot calculate what is the target. This is in general, right? There is some specific cases where you can, but in general, you cannot. So the forward model is a piece of software where you are implemented physical model and detection model. So you insert the input data, which is sample description, and then you get out of it the simulated spectra. Then you compare with experimental data by means of evaluation of consistency, which can be a visual inspection or the calculation of a chi-square. And then the optimization algorithm changes the input parameters, so you increase the consistency. This is the so-called reverse Monte Carlo approach. What MultiSIMNRA does is to expand this to multiple measurements. There is some evaluation of consistency, which is a special topic here. And if you want to learn more how MultiSIMNRA works, I recommend you to check out this paper, which was published last month. Basically, the forward model is the heart of the system. And usually the forward model for MultiSIMNRA is SIMNRA. We need a forward model for PIXE. And the point is that differently from when of the scattering techniques, where SIMNRA is widely adopted and widely trusted, and there is no PIXE software that is widely adopted and widely trusted that follows this direction. Of course, there are some interesting developments, but not compared to the use of SIMNRA. So we decided to implement our own code on this, and the direction is that given the input data, we want the spectra as simulated. So basically, by exploring simulation, we want to plan experiments and study setup optimization. We also want to enable the smoothest RBS and PIXE integration possible to avoid the best as we can the necessity of standard samples, exploit simulation to test and compare physical models, obtain the best forward model for the self-consistent analysis, and to use the same piece of code for in PCs and clusters. I will talk a little bit more about this in a few slides. So basically, we passed through many development phases. We started with conceptualization. We decided what to simulate, how to simulate. But most importantly, we took a look in the publication of other developers of PIXE codes to understand what they do best and to implement in our code. Then we moved to the database construction. We collected as many databases as we could find, so we can explore and compare the databases and even do benchmarks exactly as it is done with a non-Rutherford cross-section using SIMNRA. Then we move it to the coding. It's object-oriented code written in C++. It's a high-performance parallel computing program, and it switched to MultiSIMNRA in clusters. Now we are in the validation phase where we have some comparison with experimental data, and our intention is to release the software in 2022. So basically, as I said, we have many databases, so we can compare check how effective they are and do benchmarks with it. I point to the fact that we have some models for ionization cross-sections. We have theoretical models like ECPSSR and PWBA, but also semi-empirical ones, as the one developed in the Miguel Reis group. We have also photon ionization cross-section by Schofield to calculation of secondary emission. We also implement physical detection, physics of detection by calculating the quantum efficiency filters, including fano filters. The response function is convoluted, including incomplete charge collection and fano factor. And we also take corrections of lifetime and pileup. So as I said, PIXESim is supposed to work in PCs and on a server. Basically, it's the same code that is compiled differently. In PCs, we want this to run together with MultiSIMNRA, using MultiSIMNRA as a user interface. And the server, we want to produce data sets for training of neural networks. What is important to mark here is that we, on a cluster, we can simulate more than 25,000 spectra per second. This is possible thanks to the communication method, because the PIXESim communicates with other programs by means of message parsing. So there's no file exchange. So the disk usage is kept to a minimum. Now I'm going to show some validation measurements. This was performed in the laboratory I coordinate. Basically, we have a silicon lithium detector placed at 90 degrees regarding the beam direction. The inclination of the sample was usually 7 degrees. This is not the best way of PIXE measurement, because this is quite susceptible to roughness and sample irregularities, but the results are quite good. So here I show one example. If you are familiar to the 2015 paper on MultiSIMNRA, you are also familiar with this sample. We use this as a proof of a principle of a MultiSIMNRA. We have lots of scattering measurement to define the sample characteristics, and in that paper, it did not include the PIXE data. So now the same spectra was fitted using the PIXE information, and then we can get a very nice agreement between simulation and experimental data. I forgot to mention that the background is estimated by using digital filters. This sample is actually used to do energy calibration of the detector for the scattering techniques, but apparently it's also good to do calibration in the estimation of filters and the detector thicknesses. I just want to point out here, inside the circle, this data was fitted using the semi-empirical cross-section. Once it was fitted, I just simulated it again using a different cross-section, calculated using a ECPSSR model. And then you see in the tantalum M signal, there is a small difference also in titanium. This is exactly what I meant by testing models and methods. This is another sample. It's a self-standing gold foil. There's no not new insight over here, unless if you take into account the impurities of the sample, which was copper and calcium, coming from different sources, of course. But the point is that the two signals, the copper and calcium, are beneath the multiple scattering tail of the gold signal in the RBS data. So if you can check out, you see that my detector is not exactly in a good shape, but at least there is a good agreement between the L lines and a reasonable agreement between the M lines and between simulation and experiment. This gives us confidence that the PIXE calibration is correct for calcium and copper in the middle of the way. So this is a good example of using PIXE without a standard for calcium and copper, for example, taking the information of gold signal from RBS. So another validation data is for nickel phosphorus alloys deposited on top of silicon. This is a sample with more technological interest. There's no challenge for RBS here because nickel and phosphorus are quite well separated, but again, the impurities, there is an impurity of chlorine in this film. Don't ask me why. But the point is, you can ask me how to quantify it, because then you can see the nice agreement between silicon, a reasonable agreement, not so good for silicon and phosphorus here, giving us some confidence that the yield is correct for chlorine. This agreement is also something that we are still working on. It can be, as I said, because of sample irregularities. And the last but not least, we also do some analysis of a microscope glass slide. If you have the opportunity of using IBA to study this alignment, this kind of samples, I'm sorry for you, because this is quite hard to do. There's a lot of material inserted in the glass to increase mechanical properties. And most of this added material have some ambiguity in the RBS spectra. But this ambiguity can be solved in the PIXE spectra, and then we can fit nicely the minor elements. One thing that we learned from this sample is that we must somehow include in the analysis the concept of lower detection limit and lower quantification limits. The values that I show here in the table are the values fitted by MultiSIMNRA, but with no consideration if this is higher or lower than the quantification limit. So this is something that we must implement. So as a conclusion, PIXESim is a plugin to MultiSIMNRA for PIXE simulation. This will enable PIXE incorporation in the self-consistent analysis. And what we want with that is to increase sensitivity and reduce the ambiguity. PIXESim can also run on a cluster. It's done by means of a Python tree binding. It's a multi-thread piece of software, so it's well suited for machine learning to generate data sets, right? And the diversity of database enable benchmarks and models and methods. Test cases show the proof of principle of standardless PIXE, but there are some small letters in this contract which says that you must know the response function and the detector quantum efficiency. And the smooth integration between RBS and PIXE in MultiSIMNRA is under development with an easy-to-use graphical user interface. So I thank you for being connected and for the funding agency that supported the project in the laboratory.
Thank you, Tiago. We have time for a quick question. No, you're first.
Okay, thank you very much. Great talk. Now, it's just a suggestion. It seems to me that it's high time that different PIXE softwares are compared to each other. I believe it's the remaining of the main IBA techniques where this has not happened. So my suggestion would be contact Vivian Dimitriou at the nuclear data section of the IAEA to get some intercomparison going. Thank you.
Thank you, Nuno. Mate.
Yeah, thank you, Tiago, for this really very nice and interesting presentation. I mean, what would you say? What is the accuracy of the PIXE cross-section data that are available?
Well, Mate, I'm not ready to answer this question. The PIXESim development is quite new. We are still testing. What we have is some papers comparing experimental data and models. What I can say is that at least for PIXESim, you should avoid the use of PWBA, at least for lower energies. And ECPSSR is okay, but semi-empirical models seems to be the way to go for now.
Okay, Miguel, you have the last question.
Okay, thank you. Now I have a question and a comment. Question was about the chloride contamination, that what seemed to be there something more, but now as to comment regarding Mate question, I have shown in old times that PIXE can go down to 1% precision as long as you apply it at the same place that you calibrate it. And so if you calibrate properly your system, the uncertainties on the fundamental parameters go away, because they all get covered by the yield, calibrated yield. And once you use that, you can recover results to 1%.
Okay. Okay, I assume that was just a comment really rather than the question. Javid, I'm sorry, we really don't have time. We're 12 minutes over already and into the poster session. I don't want to subtract from the poster session. I suggest you contact Javid, Tiago outside in the poster session, tackle him there and ask him your question. Okay, well, thanks everybody for hanging on in there for the next 12 minutes. What I suggest is you all disappear over to the poster session. Don't forget to vote for your favorite poster. Come back here at 6 o'clock for the final session of the day. Enjoy the poster session. I would offer you coffee, but we haven't got any, not virtual anyway. Javid's drinking coffee, so he's already way ahead of us. Okay, so enjoy the poster session. It is in poster session room 2. The poster sessions are 51, I think 51 to 62, and 75 and 76. So go and enjoy the poster session, and hopefully see you over there very shortly.